Now we're at the bottom of page 76 to the top of page 84. The third law of thermodynamics states that at 0 Kelvin, the entropy of pure crystalline materials is equal to 0. So basically, as you have a gas, the more you cool a substance, the slower the particles start moving and the more orderly they become. There is the point at which order becomes a perfect crystal, and since the more orderly it becomes, the less entropy there is. The third law just states that there's a point where there is 0 entropy. So with our little note card here, at 0 Kelvin, which is at absolute 0, we have a delta S, or an entropy of 0. Now let's move on to a rather complex topic, Gibbs free energy. And by definition, it's the delta G is equal to the delta H minus the T delta S at a constant temperature. Delta G is a state function. Its units are kilojoules per mole, and at constant temperature and pressure, delta G will tell us about spontaneity. So just like the delta S of total of the universe is used to describe a reaction as spontaneous forward or in reverse, or at equilibrium it's not spontaneous, then we use delta G also to basically represent the same thing. At constant temperature and pressure, and only at constant temperature and pressure for the process of a reactant going to product, the following are true. And I'm going to go ahead and substitute in right here my little note card, because it basically says the same thing, but it includes the delta S total. So if you have a spontaneous reaction forward, or a reaction is spontaneous in the forward direction, then we recall that the delta S total is a positive value, but the delta G is going to be opposite. It's going to be a negative value. If the reverse reaction is spontaneous, then the delta S total is negative, and the delta G is going to be positive. And then at equilibrium, both the delta S total is equal to 0 and the delta G is equal to 0. So you'll notice that when it comes to describing spontaneity, they have perfectly opposite signs, and then at equilibrium, they both are going to be equal to 0. So let's kind of define, what is delta G? It's going to tell us how much energy, because it's called Gibbs free energy, how much free energy is available to do work. Many reactions must generate heat in order to make the process spontaneous, and delta G is a measure of the remaining energy that is available to do work. So delta G tells us if a reaction is spontaneous based on the amount of energy available for the reaction to do work. So let's consider the following reaction. Hydrogen plus nitrogen yields ammonia. And it's going to reach a state of equilibrium eventually, but it doesn't start out that way. It starts out where the forward reaction is occurring, and it might get to a point where a little bit of the reverse reaction needs to occur until it finally reaches that sweet spot where it is in a state of equilibrium. So let's take a look at this graph to kind of demonstrate that. Here would be where the reactants are, and spontaneously from this point, the reactants are forming into products. And so you'll notice I'm going down the graph, and so the delta G is negative. And it remains negative until I get to, and let's just say we pass point 2 and we go up to point 3. And now let's say some of the reverse reaction is occurring where my products are turning back into reactants. So here, the delta G is positive, because the reverse reaction is true. And then at number 2 is when we're in a state of equilibrium and the delta G is equal to 0. So standard Gibbs free energy changes. Just as for enthalpy, we are going to use this equation in order to calculate the delta G of a reaction. And so I'll kind of bring this in to remind you that to calculate the delta H of a reaction, we take the moles times the delta H formation of each product and add them together, take the sum, and we subtract the sum of the reactants delta H of formations times their stoichiometric coefficient. And so we do the same thing for delta S, and so you can do the same thing for a delta G. You can also calculate a delta G with this equation if you are not given all of the formation values for the products and reactants. We could use the delta H of the reaction minus the temperature times the delta S of the reaction to get the delta G of the reaction. So N and M are the product and reactant stoichiometry, or coefficients in the balanced equation, and the degree symbol is letting you know that we are at standard conditions, so 1 atmosphere, 1 molar, and 298.15 Kelvin, and the little f stands for the formation reaction. So, and this is just to remind you that you can use the same type of equation for calculating entropy. And notice you're using absolute entropies instead of differences in entropies. So now let's do an example, 19.23. And the question is, calculate the delta G of the reaction for this reaction using the delta G of formation values that are provided for you in the table. And our reaction, we're going to take the product's delta G of formation values, and we're going to subtract the reactant's delta G of formation values. So we're going to have the delta G of water plus 1/2 times the delta G of oxygen minus the reactant side, the delta G of hydrogen peroxide, which is provided down here. So when we enter these values in, we're going to get the delta G of water, which is negative 228.57, and it's going to be times 1 because the coefficient of water was 1. And then we're going to add that to 1/2 times the delta G of oxygen. However, because oxygen is in its standard state, the value for this is going to be 0. And then we're going to take these two, combine them, and we're going to subtract the delta G of hydrogen peroxide, which is negative 105.48. And we'll notice here that the negatives turn into positives, and they essentially add together. So we'll take negative 228.57 and plus 0, basically, and then plus 105.48. And we get a value of negative 123.09. And notice that this is in kilojoules per mole. And because this value is negative, we have a negative delta G, which means that the forward reaction is spontaneous. Now we'll look at example 19.24, where you're going to calculate the delta G of the reaction using the values in the table, and we are given in this case the delta H values and the delta S values. It's very important to notice the difference in the units. The delta H is always given in kilojoules, and the delta S is always given in joules. You're going to want to convert your delta S to kilojoules in order to solve this problem. Remember that we were given the equation, secondary equation, delta G of reaction is equal to the delta H of reaction minus the temperature times the delta S of the reaction. So what we're going to have to do is first determine what is the delta H of the reaction. And we're going to take the products, so water has a delta H of negative 241.82, remember that's kilojoules, and we're going to add it to 1/2 times the delta H of oxygen, which we're not given a value, so you assume it is 0. And we're going to subtract the delta H of our product, which in this case is negative 136.10, and notice that that becomes a positive value. So let's go ahead and do this math. So it gives us negative 105.72. And that's kilojoules per mole. Now we're going to do the same process but determine the delta S of the reaction. And what I'll do is convert my final answer from joules to kilojoules. So we have H2O for my delta S is 188.83 plus 1/2 the entropy of the oxygen, which is 205, minus the entropy of my reactants, which is 232.9 equals. So we have 188.83 plus 1 divided by 2 times 205, and then that is going to be minus 232.9. And I get a positive 58.43. So positive 58.43. Notice that's joules. In order to convert it to kilojoules, I need to divide by 1,000. And so this value divided by 1,000 will give me my kilojoules. Now I can use this equation below. The delta G of the reaction equals, and we have the delta H and we have the delta S, but what about the temperature? Remember that because we see the degree symbols here, that this reaction is at standard states, and we were told that standard states is 1 atmosphere of pressure, 1 molar, and 298.15 Kelvin. And so that is our temperature, and so you're expected to be able to determine that even though you weren't given it. So now we're going to insert our information into the equation. Delta G of reaction equals delta H of reaction minus T delta S of reaction. So we get negative 105.72 kilojoules minus 298.15 Kelvin times 58.43 divided by 1,000 kilojoules. When we enter this into our calculator, we'll get negative 105.72 minus 298.15, and that's going to be times 58.43 divided by 1,000. And we're going to get the same value as before because we're using a different way to calculate the same problem. And so you get negative 123, this is kilojoules per mole. And again, because that's a negative value, it means that we are spontaneous in the forward direction for this reaction.